somewhere in a field left untouched for one growing season. A plant that feeds more of the planet than almost any other quietly fails to come back. Not because of drought, not because of pests. Because its seeds are sealed shut inside a husk that will not open on its own, locked to a cob that will not break apart. And nothing sheds them onto the ground the way every wild grass on Earth has managed for 100 million years. Corn cannot plant itself. It has not been able to for thousands of years. And the reason is one of the strangest transformations in the entire history of agriculture. To understand how a plant lost the ability to survive without people, start with what it used to look like. Around 9,000 years ago, in the seasonally wet lowlands of Mexico's Balsas River Valley, people were harvesting a bushy, many-branched grass called teosinte. Its seed spikes were small, hard-cased, and built to shatter apart the moment they ripened, scattering kernels across the ground exactly as wild grasses always have. What grows in a modern cornfield looks almost nothing like it. One or two thick stalks, topped by ears carrying hundreds of soft, exposed kernels that stay locked to the cob no matter how ripe they get. In the 1930s, geneticist George Beadle crossed the two plants directly and counted how many of the offspring looked like one parent or the other. From those ratios alone, he guessed that as few as 5 genes might separate a wild grass from a domesticated crop. Decades later, John Deblee and Adrian Steck reran Beadle's cross with tools he never had, mapping the actual regions of DNA responsible. Beadle had been right. A handful of genes, among them one called teosinte branched 1, controls whether a plant grows dozens of thin branches tipped with pollen or a few thick stalks tipped with seed-bearing ears. Change that one gene, and a bushy grass starts growing into something closer to corn. A plant that could no longer feed itself still had to learn how to feed people, and that took a second invention. Raw, unprocessed corn has a problem that has nothing to do with its genetics. The niacin locked inside its proteins is barely usable by the human body, and a population that leans on corn as its main staple without treating it first risks pellagra, a vitamin deficiency disease. Sometime around 3,000 years ago, in Mesoamerica, someone worked out the fix. Soak and cook the kernels in water mixed with lime, or with ash from the cooking fire, then wash and hull them. The process is called nixtamalization, and by most accounts it was developed and passed down by women, generation after generation, long before anyone understood a single word of the chemistry involved. The lime does more than unlock nutrition. It loosens the tough outer hull, transforms the flavor, and destroys the vast majority of the mold toxins that untreated corn can carry. A pot of kernels goes in pale, hard, and barely digestible. Comes out soft, fragrant, and safe to build an entire diet around. Once corn was edible, the next question was how to grow enough of it without exhausting the ground it grew in. Picture a low earthen mound, corn stalks rising from its center, bean vines spiraling up around them toward the sun, and squash leaves spread flat across the soil at the base, broad enough to choke out anything trying to compete for light. That system has a name across many indigenous nations of North America: the Three Sisters. It began with the Haudenosaunee, the people of the Longhouse, and was independently adapted by the Cherokee in the southeast, the Mandan and Hidatsa on the plains, and the Hopi and Zuni in the arid southwest, each version tuned to its own climate. The engineering works in 3 directions at once. Corn gives beans something to climb. Beans host bacteria in their roots that pull nitrogen straight out of the air and feed it into the soil, replenishing exactly what corn depletes fastest. Squash shades the ground, holding in moisture and shutting out weeds. A modern replication of the practice found the 3 grown together produced more food energy and more protein per acre than any one of them grown alone. give a farming system that much of an edge, and eventually it stops feeding villages and starts feeding cities. Near the Mississippi River, across the floodplain now called the American Bottom, a city rose that had no equal anywhere else in North America north of Mexico. Cahokia, at its peak around the year 1100, held somewhere between 10 and 20,000 people, its central plaza dominated by earthen mounds built basket load by basket load, its granaries filled by maize grown in some of the richest floodplain soil on the continent. The city's founders had brought nixtamalization with them, and for its first century and a half, Cahokia's maize was processed exactly as Mesoamerican tradition demanded. Then, sometime around the year 1200, the practice stops showing up in the isotopic record. Skeletal remains from that later period show iron deficiency anemia and dental enamel, defects consistent with real nutritional strain. Researchers have not proven that alone brought the city down. What finished Cahokia over the following 2 centuries was one of the most severe droughts to hit the region in 1600 years, landing on a population that had made itself dependent on one crop's yield. By 1400, the city that corn built was empty. Corn's story does not stay in the Americas for long. After 1492, Portuguese traders carried maize out of the Americas and into West Africa, and from there it moved fast. By the early 1500s, corn was already growing around the Mediterranean. Its short growing season and its tolerance for wildly different climates meant that within a couple of generations, a crop that had existed nowhere outside Mexico for 9,000 years was a staple crop on 3 continents at once. The most recent chapter of corn's transformation had nothing to do with indigenous farmers at all, and everything to do with a laboratory. In 1908, 2 scientists working independently, George Shull and Edward East, discovered that crossing 2 inbred corn lines produced offspring that dramatically outgrew either parent, a phenomenon called hybrid vigor. A young Iowa farmer named Henry Wallace took that discovery and turned it into a business. Using controlled pollination, he produced one of the first commercially successful hybrids, entered it in yield trials starting in 1921, and by 1926 had co-founded a company built for one purpose: selling hybrid seed corn every single season, because a hybrid's own offspring will not reliably repeat its parents' traits. Field trials through the 1920s showed those hybrids out-yielding traditional corn by 10 to 20%, while national average yields at the time were stuck barely above 20 bushels an acre. Corn had been re-engineered twice now, once by indigenous farmers over thousands of years into a plant that could not reseed itself, and once more by 20th-century genetics into a plant whose own seed, in most fields today, gets thrown out rather than replanted. A wild grass on a Mexican riverbank once scattered its own seed without any help from anyone. What grows across the American Midwest now cannot do that, has not been able to for millennia, and depends on someone deciding every single spring to plant it again. Along the way it fed a Mississippi River city into existence and then outlasted it, crossed an ocean in a single lifetime, and got re-engineered a second time by a farmer's son from Iowa. So here's a question worth sitting with. When a species becomes more useful to us, the more dependent on us it grows. Which one of us is actually in charge of that relationship?